The project grades went out, so there's a few people who had questions about them. Any questions about anything in the class, anything you need to know about? All right, we're going to start our next unit today. I don't actually, I guess section, unit, I'm not really sure how we call it, but like the next big module of the course, which is called uncertainty. So up to this point, we've been really talking a lot about search and state spaces and how we can walk around in state spaces. And we've been talking a lot less about the scoring function. How can we know something about the world and whether we've gotten to a good place or a bad place in the world, and what does it even mean to know anything at all about the world? And so this section is called uncertainty because the techniques that we're going to be using to make our scoring functions for our AI algorithm and really for doing a lot of reasoning as an intelligent system are really based on modeling and reasoning about uncertainty. So that's the sort of focus of the next couple of weeks of the class. So before we do that, though, I wanted to share with you guys some of the highlights of this discussion post exercise that we did. I had a lot of fun reading what you guys came up with, and I thought it would be fun to go through some of them together in class. So this was one of my favorite ones. Who came up with this one? Are you here? Cool. So thanks. So writing code to write code. So the idea here is we're going to make a state space to generate all the possible programs. Let's just say Python, because we're all coding in Python today. And your actions are composing, removing, or editing lines. The transition model causes the code to change. And your cost function is whether you pass your test cases or not. So you think if you run this on Pac-Man, will it find breadth first search?
Yeah.
Eventually, yeah, it will. So there's actually a lot of research in techniques for doing this in more efficient ways. So as you can imagine, the state space for all the possible programs in Python is pretty big. So doing uninformed search is not really going to quickly lead to a good solution. But people do, there's actually a section in the book, and I think it was covered last year, people do what's called genetic programming, where it's a version of simulated annealing in the space of programs, and you're kind of editing and making changes to your code, and the output is a Python program. So I think, so I think this is a fun one because it's very meta, and in some sense, this is what we're all trying to do in AI. Like we're trying to come up with an intelligent agent, and sometimes that involves computation. So we're trying to figure out what computation we need to do to act intelligently. Another one I liked, somebody came up with a robotic nutritionist. So based on the food at the dining halls at Brown. The idea is to come up with the best meal plan that's both healthy and also satisfies your eating preferences. So the state space is all the food that's served. You can just pick a dish, and then the cost function is some combination of the total calories so far and how much the person likes it. Who did this one? Are you here? No? Yes. Awesome. Thank you. So the reason I like this one is because, and there's another one I'm going to show you about medical diagnosis, is even though it seems kind of fanciful about having something help you pick your food, these kinds of health applications I think are one of the most exciting unexplored areas of AI. So obesity and diabetes and these associated metabolic diseases are increasing dramatically, and they have like if you get diabetes, my dad has diabetes, and every single day he's got to give himself a shot of insulin, and he's got to check his blood sugar, and if he doesn't do that, this has happened to him a couple of times, your glucose gets wrong and you go into this condition where your glucose drops really low, you lose consciousness, you start to get disoriented, and if you don't drink some soda or like orange juice, you have to put sugar into your body, you die. So there's like these near-term effects, and also it puts you in increased risk for strokes and heart attacks. My dad has had both, and lots of people have this kind of issue in the United States today, and lots of other Western countries too. So something like this, while it seems fanciful, people are doing a lot of research to try to figure out ways to improve our diet. It's kind of like us versus big sugar and big agriculture here. How can we eat in a way that preserves our health so that we can live long, healthy, happy lives? So I like this one. This is the other one that was sort of related to healthcare, intelligent medical system diagnostics. So this was actually one of the first big uses of AI. People made these things called knowledge-based systems, where they talked to doctors and they made up this big knowledge base of all the diseases and all the symptoms they could think of. And then they did search, the same search algorithms you guys are doing. You would input the symptoms, and it would chunk through the knowledge base and try to find the diseases that were consistent with those symptoms. What's interesting about the sort of classical AI formulation, which is like the search-based formulation, is at the bottom you kind of get this diagnosed disease. You just get this list of diagnosed diseases, but really that's not what happens. Like when you come in to the doctor and you have a fever and a sore throat, what could that be? Like as just sort of naive people, like strep throat. What else?
Mono.
What?
Mono.
There we go. What else?
A cold.
A cold. What else?
Cancer.
Cancer.
Lupus.
So there's a pretty big set of diseases that could be caused by any particular set of symptoms. So like let's just say fever and a sore throat. What do you think is the most likely thing that's wrong though? Using our intuitions about medicine. What would your mom say if you called your mom up and said? Cold. Yeah, most likely you've got a cold. So we're sort of going to, so in this sort of classical AI version of the problem, what you're going to return is just a list. It's going to return lupus, even though it's not very likely maybe that you have lupus. Just knowing the epidemiological characteristics of the brown community, right? But we know that even though it's possible that you could have some kind of rare disease like lupus or cancer, it's much more likely if you present with a fever and a sore throat that you've got a cold. And so what we're going to talk about today, we're going to kind of move in this direction of how can we quantify that? And how can we move from this symbolic world to a more general world where we can actually have degrees of belief about the world and do consistent reasoning about our degrees of belief, and that's probability. The other one I wanted to highlight was sailboat pathfinding, because I'm a sailor, so this is near and dear to my heart. If you, I don't know, how many of you guys are sailors? Yeah, a bunch of you, good. And who did this one? Are you here? No? Shy?
It was a similar one.
It was another sailboat one. I like this one better because it broke. I saw that there were two. It broke it out into state spaces and action spaces in a neater way. But I liked that there were two. Like there was two sailors in the room. Two people who actually posted sailboat. And there's actually a robotic sailboat competition. So if you want, you can make a robotic sailboat. It was run in Boston Harbor this year, hosted by Olin College. And all these different teams made robotic sailboats. And so the trick with sailing is you can't just go where you want to go in a straight line because the wind is blowing and you can only go up to 45 degrees to the wind. So if the wind is... What's that?
You can go closer than that in your sailboat.
Well, it depends on your sailboat. So as an approximation. So if the wind is going this way and you're a sailboat, and this is your sail, let's see. You cannot go straight into the wind, for sure, right? But it turns out that you can go, if you go at an angle, then like the physics of this, your sail kind of goes like this, and you can go this way. If you have to know Newtonian mechanics and stuff, and there's a centerboard that kind of redirects the force. And then if you're here and you want to be here, you can't do this, but you can do this, and then you can do this, and then you can do this, and then you're here. So the path planning problem is kind of interesting because you can't just go where you want to go. You have to respect the wind and the water. And somebody who posted a comment also pointed out that we don't even know what the wind is going to do. So if the wind, so I sail a lot in the Charles River Basin near MIT, and there's all these tall buildings. So what that means is you get these puffs when the wind comes between the building, and then you're in the shadow of a building, and now there's no wind anymore. So it might be the shortest in distance, but there's no wind. So there's this uncertainty that we have to model in the world. We don't really know when there's going to be a puff and when there's not going to be a puff. And even though maybe we could know the wind shadow of the buildings and stuff, it's actually pretty hard to predict that. There's this kind of fun, in most places, and there's this fun place, there's the Mass Ave Bridge, so it looks like this, with these pillars. This is the water. And if you sail, if you're the sailboat right here, and you sail along the bridge, you'll get in the shadow of the pillar, and then you'll get out of the shadow, and you'll get a little puff, and you'll go fast. And then you'll get back in the shadow, and you'll go slow. But most places on the river, it's hard to predict what the wind is going to do. So we have to handle the uncertainty about that if we want to make an optimal plan. So I hope this was fun. Was it fun?
Yeah.
Yes? No? Comments about that? Did anybody have any feedback for that exercise? Because I sort of trying to decide whether we should do it again or whether it was, not useful. What's that?
It was cool.
It was cool?
Like, see all the different things you do.
Yeah. I sort of think that this kind of brainstorming about how we can use AI and formalizing the problems is a useful exercise. So I think we will. So I'm not hearing anybody complain. Speak now, forever hold your peace. So I think we probably will do a couple more of these discussion post exercises because I think it's kind of fun. Okay, and then the last one I wanted to put up is nice because it leads into what we're going to discuss in today's class. So this is proving or disproving a mathematical theorem. So the idea is you have your state, which is all of your previously proven theorems, and then your actions, which are basically your rules of inference. So if you have two things, like you might know that A implies B and A is true, then you could infer that B is true. These are the rules of deductive inference. And then your cost function, maybe you want to find the shortest theorem or something else. And your goal state is whether you've actually been able to show that this theorem is true or not true. And people have done lots of work in making these automated theorem provers. And we're going to do a little bit of that today when we talk about Boolean logic. So, and this is really about representing knowledge and using your knowledge just by thinking to get more knowledge. So you have some set of things which are true. Can we reason about them to get more things which are true? So it kind of feeds into today's lecture. So we're going to sort of switch gears now and start to talk about uncertainty. So how many people did the reading? I'm curious so far. Okay, not so many of you. So the reading in I sent mail. Did you guys get my mail about the reading? Yeah? No? Did anybody not get my mail about the reading? Okay, so that was interesting. Like the negation was not the inverse of the people who raised their hands. So for the most of the classes, there's reading assigned, and I think of especially when it's from the textbook, I think of that reading more as a reference. So if you want more detail, if you didn't understand something, you want to take another look, if you're doing the project or the problem set and you want a reference, the textbook is there to provide backup. But for a few of our lectures, the reading is really important. And we already had one of those when we did the Bronavon paper, where we read the research paper, and I'm planning on doing a few more lectures like that. And these two lectures today and next Tuesday on E.T. James's book, I also think the reading, actually sitting down and doing the reading is really important, and I think you'll find it interesting and fun. I don't know if anybody who did do the reading want to tell me if they thought it was interesting and fun or boring and confusing or something else. Yes?
I thought it was interesting and fun, although on the website it says that the readings for next Tuesday and Thursday, I think.
Really?
Yeah.
I thought I checked. Well, I sent the email with the link, so it's okay if you well, anyway, I think that you will get the most out of these two lectures if you do the readings. It's just 2 chapters, it's 60 pages. It's pretty dense, but it's kind of funny. He's kind of snarky, and it gives this interesting history of where probability comes from deriving it as a generalization of logic. And I think it's really worth going back to these kind of first principles before we dive into particle filters and Bayesian networks and stuff like that, because it just helps you get off on the right footing. So we're going to go through this in maybe it seems kind of, some of it might seem kind of elementary, but I think if you think of probability in this way, it will serve you well in your future endeavors in computer science. It's kind of, in my opinion, it's the right way to think about probability. So here we go. So this is sort of our act rationally, and we're going to think today about the scoring function. What does it mean to be able to assess how good an action is in the world? How can we assign a number, some kind of real number, to something about what we believe about the world being true? Okay, so to make this concrete, I thought it would be kind of fun to think about an example of something we want to prove about the world. So this is President John F. Kennedy. He was assassinated. This is a photo was taken a few seconds before he was shot by a sniper in Dealey Plaza in Dallas, Texas, in the 1960s. And ever since that happened, there's been a lot of controversy about what happened. So kind of what we know from history is that he was shot by a sniper on November 22nd. About 70 minutes later, the Dallas police arrested this guy named Lee Harvey Oswald. He was actually arrested for shooting another police officer fatally, Officer J.D. Tippit, but then he was charged with the shooting of JFK. And then just 2 days later, Oswald himself is fatally shot by Jack Ruby. And ever since that time, there's been all these questions. Was Oswald acting alone, or was there a conspiracy? Who's heard of the grassy knoll? Maybe you've heard of the grassy knoll. There's like this question, was there another sniper on the grassy knoll? So we're pretty sure that Oswald did shoot JFK 3 times, or at least he fired 3 bullets at JFK. He left the rifle up in the building, which is called the Texas Book Depository. But people don't know how many shots were actually even fired, right? So if you they did interview lots of witnesses, and the numbers of shots reported by witnesses ranges from like 1 to 7. And I think the most common is 4. So there's, it's not really clear what happened there, and they have evidence from the bullets, so in the injuries of the people, but what they think happened is that one bullet can go through multiple people and cause multiple different injuries, and they might not even be able to find the bullet. So like if it landed in the crowd in the street somewhere, maybe it just disappeared. So there's a lot of uncertainty about what actually happened in this scenario. And people have argued about it based on evidence. And somehow what we do is we take these facts and we weigh them in our minds. We do some kind of computation. And then we come to some conclusion. So who thinks Oswald acted alone? I do. Who thinks that JFK was shot as part of a conspiracy? Few of you, okay. And who doesn't know? Who's never heard of JFK? Who's never heard of JFK? Who doesn't know? Who just has no idea what happened? Okay. Who didn't raise their hand any of the previous? What do you think?
I don't have enough information to really know.
Okay. All right. So what's that? Yeah?
It wasn't, well, in theory, the government could release their files on this.
Yes. So maybe we'll jump to that. I was going to do that at the end. But yes, so the government released their files. So immediately after the assassination, the government, Lyndon Johnson was JFK's vice president. He formed something called the Warren Commission. Warren was the Chief Justice of the Supreme Court, and he headed it. This is so if you guys remember the 9/11 Commission report, this is like that, a bunch of government people wrote a book. It's a book. It's like this thick. I read it, about what happened. And this book they weigh all the evidence. They do ballistic tests, and they talk about the autopsy of JFK, and they conclude that Lee Harvey Oswald acted alone in killing Kennedy and wounded. He also, when he did this, he wounded the governor of Texas, who was in the front seat of the car where JFK was, and that Jack Ruby also acted alone when he killed Oswald 2 days later. About 10 years later, there was lots of controversy about this. Something called the United States House Select Committee on Assassinations investigated the assassination of JFK as well as the assassination of Martin Luther King. And they concluded that scientific acoustical evidence establishes a high probability that 2 gunmen fired at President John F. Kennedy. So they thought that Oswald actually fired the bullet that killed him, but that there was more than 1 gunman, and therefore JFK was killed by a conspiracy. This really mattered at the time. I guess I don't know if it really matters now, 40 years later. But at the time, this was really important because we were in the middle of the Cold War, and so if there really was a conspiracy, maybe Russia was behind it, and maybe we should, escalate our if Russia had assassinated the president of the United States, that would have had a large negative effect on international relations. Whereas if Oswald is just a lone nut, then we should really be nice to Russia and not start a nuclear war, right? So people were really concerned about this, and it turns out that it's really I don't want to get too much in JFK, but it turns out Oswald actually lived in Russia for 2 years. He defected to Russia, so there's a lot of interesting little details about this whole assassination, about this whole story, which we don't want to get into too much into. But I guess what I want to say is, for an important problem like this, how can we make a decision about what really happened? What does it even mean to make a decision? So do you think we can actually know what happened 40 years ago on that day in Dealey Plaza? Yes. How can we know?
Eventually.
Eventually.
The information is somewhere.
The information is somewhere. You think it is?
Well, there was all sorts of light and sound and things going on at the time. That's
There's actually a video
distributing. Oh, really?
of the assassination, yes. It's called the Zapruder video, and they actually number the frames because it's in the 60s, so it's not like your iPhone video. And they actually show the shots hitting the president and stuff. But we still don't know how many shots were fired. There's no sound in the video. There's this other audio recording that if you listen to it, you can't really tell. But the House Select Committee concludes that scientific acoustical evidence establishes a high probability that two gunmen did fire. So different groups are looking at the same evidence and coming to different conclusions about it. And I actually would argue that we can't ever know for sure. Even if new evidence comes to light, the conspiracy theorists are going to tell us it's all faked, right? That the people who assassinated JFK because they didn't want to have his liberal agenda continue to go through, faked all this evidence so that we would think, dupes that we are, that Oswald acted alone, and they got away with literally the murder of the president. Whereas people who think that Oswald acted alone will see this evidence and think it confirms their beliefs about what really happened that day. So I will argue that we can never know for sure what happened, but we can assign we can have some kind of quantification about what might have happened. We think some things are more likely than other things. So here's something that could have happened. Like maybe some aliens came down and landed on top of the Texas School Book Depository, and they shot JFK. Does that sound pretty likely or pretty unlikely? pretty likely? Yeah. Pretty unlikely. So we can assign some kind of quantification. We think some things sound better than other things based on evidence. What's that? Okay. I'm happy to take questions. And what we're going to talk about today is what does it mean to try to formalize our beliefs about the world so that we can run computation on them, so that we can do reasoning. And then we're going to talk in then the next lecture, what does it mean to assign numbers to having degrees of beliefs of things about the world and update those numbers based on evidence. And that's going to get us to the rules of probability, which underlies a lot of the power of modern AI. So with that to motivate us, let's talk about deductive reasoning. So what is deductive reasoning? Have you guys seen deductive reasoning before? Yeah?
Axioms and rules of inference.
Yeah, that's right. So we have these axioms. What's an axiom? Yeah?
Something that is fundamentally true.
Is it fundamentally true?
I guess it's just a rule.
Something that we take to be true.
Something that we take to be true.
Right.
Something that we decide we're just going to pretend that it's true. What's a rule of inference? Yeah?
A way of getting from an axiom to a theorem, like some step which takes previous knowledge and produces new knowledge.
That's right. So we get some kind of thing that we think is true, and then we have some rule for transforming it. Maybe we're combining two different sources of information, and then we're going to get to new knowledge. So here's an example of a rule of inference. So this is sort of an abstract form of it. If A is true, then B is true. So for our JFK example, something like this might be, if 4 shots were fired, then JFK was killed by a conspiracy. So if we could somehow know that 4 shots were fired, then we know that there has to be more than one gunman. That make sense? I'm sort of asserting this. I'm not telling you, this might not be really true. But we might write this down as a way of formalizing our knowledge about the world. So now something else that we could say is A is true. So then this lets us apply a rule, an inference rule. So what can we infer from these two statements? B is true. Does that make sense to everybody? Therefore, B is true. Does that not make sense to anybody? Does anybody want to argue with me about that? No? All right. So if A is true, then B is true. A is true, therefore B is true. So if 4 shots were fired, then JFK was killed by a conspiracy. 4 shots really were fired, therefore JFK was killed by a conspiracy. So here's another one. If A is true, then B is true. B is false. So what can I assume about that? What does that let me infer?
Is something.
A is false. Yeah, this is the contrapositive inference. These have fancy names. This is called modus ponens. So we can say, so if 4 shots were fired, then JFK was killed by a conspiracy. If JFK was not killed by a conspiracy, then 4 shots were not fired. So it lets us make these deductive rules. We would like, and these rules were proposed by Aristotle, these rules of inference. And so they've been around for a long time, and they're very venerable. However, they don't really let us do everything we want to do in a world where knowledge is uncertain. So we don't actually know how many shots were fired in Dealey Plaza that day. We don't know. People think, like I said, if you asked people who were physically present and heard it, you get a very large number of different estimates. It's very echoey, so when a gunshot's fired, it echoes against the buildings and stuff. And people just weren't able to perceive it. So we don't know for sure how many shots were fired that day. We have different pieces of evidence. We have the shells that were ejected from the rifle that was found in the Texas School Book Depository. And we have the actual bullets that were found in JFK's body and in the vehicle that they were in. And then, of course, we have these witness reports. We have the camera recording and stuff. But we don't know for sure. So what we're trying to do instead is what the book refers to, what James's book refers to as plausible reasoning. So if A is true, then B is true. And then we know that B is true. Our conclusion is that A is more plausible. So is this inference licensed by the deductive reasoning? No. So if A is not true, if B is true, A could be either true or it could be false. So we don't really know which is the case. Deductive reasoning doesn't tell us anything about it. But somehow our intuition's kind of like this, right? Like if B is true, then one of the ways that we think that B could have been true is because A was true. So we take that to be evidence that A was actually the case. And so James gives a few more examples of this. A is true, then B is true. If A is false, what does that tell us about B?
Probably not.
So what does it tell us deductively first? Nothing, right? So if we write out the truth table for implication, it doesn't tell us anything. If A is false, B could be true or it could be false. We don't know. But in terms of plausible reasoning, we kind of like the idea, if we think that this is true, that if A is true, then B is true, and we find out that A is false, somehow it seems like A should be less plausible. B, sorry. Yes, sorry. Let me fix that. Somehow, B should be less plausible. Does that make sense? This kind of intuition where the logic doesn't really match what our intuition says is true. So even though the logic is kind of giving us this power, because if we can actually prove something deductively, we can be really sure, like if we believe our axioms, which we just decided we're going to take to be true, and we trust our rules of inference, we can be sure that we can believe all the conclusions that deductive reasoning gives us. But it seems like it's somehow throwing away some of the information that we have about the problem. So in the case of this JFK thing, even though we don't know how many bullets were fired that day, we know we're pretty sure it wasn't 0. And maybe we'll put like a Gaussian distribution over our belief, like 0 is, I guess it's not Gaussian because it's a street. So here. So if this is 0 bullets, this is 1, 2, 3, 4, and nobody thinks there were 5, let's say. We're somehow throwing this away, because if we don't know for sure how many bullets are fired, we can't even get started with our deductive reasoning. So what we're trying to do, what James is trying to do, is motivate why we need to do something more general than logic, to take into account this information that we're not sure about in the world. So his final example is if A is true, then B becomes more plausible. B is true, therefore A becomes more plausible. So because B is more plausible, because B, is this wrong? This might be wrong too. So if B is true, one of the reasons that B could be true is because A caused B to happen or something, right? So this is sort of our intuitive desiderata for plausible reasoning. So what he's doing right now so in the reading, what he does is contrasts the deductive reasoning, the deductive logic rules, which you really can't argue with. Like if you don't buy that, then there's not. It's really hard to reason consistently about anything if you don't buy the deductive logic rules. But he's contrasting them with these rules, which aren't licensed by deductive logic, but which we as people seem to use all the time to infer a lot of really useful things. And what he's going to try to do is derive quantitative ways to compute, to license these kinds of inferences in a mathematically rigorous way. So that's going to be the chapter 2. But before we get to that, what I wanted to do was dig a little bit more into the deductive rules, because all of the stuff in probability that we're going to do is building off of this sort of deductive base. So as we talked about at the beginning of class, if you have a knowledge base and you have these inference rules, proving more things about the world looks just like the search problems that we've been formalizing, right? So we have an initial state, we have actions, which are our inference rules, our results update the knowledge base with the new things that are true, and our goal is that the knowledge base contains the sentence we're trying to prove, or maybe it contains its negation. So we're trying to, without worrying about this uncertainty, come up with things which are true about the world. So in the way that people formalize these statements is using Boolean algebra. Have you guys seen Boolean algebra before? Some of you? About half of you. Okay. So people use different notations for this. Basically, this is a way of writing down these rules of deductive logic. So A, B, where they're basically kind of multiply together. So A and B are propositions, like 3 shots were fired or Oswald acted alone, that have some truth value. They can be true or they can be false. And then if we have 2 propositions, then we can take the and of them, so A and B. So A and B is true. It's defined to be true if A is true and also B is true. Otherwise, it's false. A or B. So either A is true or B is true. Then this expression is true. Otherwise, it's false. If both are false, it's false. And A implies B. We talked a little bit about that. So this is true if A is true and B is true, or if A is false. And then not A. So it's true if A is false. So unary operators. Are these all the operators we could have?
No.
What are some other ones?
XOR.
XOR. What's XOR?
Exclusive OR.
Yeah.
Both are true, then the statement is false, but if only one or the other is true, then the statement is true.
Right.
Both are false, then the statement is false.
Yes. So exclusive OR. Does that make sense to everybody? If both are true or both are false, it's false. But if one or the other is true, then it's true. And when we say or in English, usually we mean exclusive or, even though logical or is true if either one or if both are true. What's another one?
NAND.
What?
NAND.
NAND. Yeah, what's NAND?
Negation of AND.
Negation of AND, yeah. So it's true if A and B is false. That make sense? Any others?
Nor.
Nor, yeah. Yeah, it's
Nor
true.
the nor.
What's that?
You could do nor.
What's that?
I'm saying it's just like and.
Yeah, it's just like NAND. So nor is not and. So it's true if A and B is false. So we can come up with all of the different 2 argument operators. We can just write them all down as a list. So what's I don't know. So I don't know if you guys cover like this in previous CS classes, but it's kind of an aside to what we're going to talk about next. But I wanted to cover it anyway because I think it's important to think about the minimal set of operators. So we can come up with lots of these different operators. There's a finite number of them. There's not too many. How many do we really need? One. Yeah. Which one? NAND or NOR. Yeah. So what does that mean if we only need one? What does that mean sort of computationally? Somebody else. Thank you, though. Yeah.
All the other operators can be derived from a single one.
Yes, all the other operators could be derived from a single one. So I thought we could do, programming-wise, is just do that empirically. I think I have my, yeah, NAND and NOR. So let's just see what that looks like in operators.py. All right, so here is my little program. Let me make it big. So what's happening right here, let me make it this one big too. Options. How's that? So what I'm doing in the code here is I'm going through all the values that A and B could take. A could be true, it could be false, B could be true or false. And then I'm computing some value, which is one of these operators of A and B. And then I'm printing out A, this is just doing padding, B and V. So here it is. This is my, oh, I have to print operators new, sorry. Operators new.py. So here's the truth value for A, the truth value for B, and the result. That makes sense to everybody? And what's being printed right now is not A and B. So the first thing I'm going to do is make a function, NAND A, B, which is going to return not A and B. We'll just call it NAND A, B. So if we can define everything in terms of NAND, what we should be able to do is write functions, any Boolean, so the claim is that we can write any Boolean logic function we want in terms of just NANDs. So let's pick one. Let's start with not. Good. You guys are on top of me. So I'm going to have to call it underscore not because we have a not in Python already. So I'm just going to. So it's going to take one proposition. And so I could, of course, just call not A and get the answer using Python. But I'm only allowed to use NAND. So how can I do that? Somebody who hasn't talked yet. Yeah.
NAND AA.
Yes. So I can call NAND on itself. All right. That's going to break my... So I'm just going to tell it to return V equals not A. So we're going to see it twice.
Underscore.
Underscore. Yes, thank you. So it calls my thing. All right. So ignore the B column. So A is true. Is this not A? Yeah. And B is false. And this is not A. Does that make sense? Does everybody kind of get why that works? Do we want to write out a truth table maybe, or are you going to trust me? Trust me? Okay. So basically, we're just taking A, A NANDed with itself. So if A is true, then AND of AA is true. So NAND of AA is false. If A is false, then AND of AA is false. So NAND of AA is true. So it's negating. So let's do a two-argument one. So let's do or. Okay. Or of A. So how do I do that? Besides, oh sorry, yeah, A, B. So I could of course do A or B. That would work, but we're going to do it just with NANDs. Somebody else, but thank you. What's that? De Morgan's laws. All right.
So if you take not NAND of not A and not B.
We can't use not, can we?
Well, NAND of NAND A, comma, NAND B, comma, B.
Yes. So let's try that. Oh, sorry, A, B. Thank you. All right, does that work? So A is true, A, B is true, B, A is true, A is false. Yeah. So let's do one more. Let's do implies. Implies A, B. So how do we do that one in terms of just NAND?
False, A is false, or A and B.
Can we use ors and nots?
No, we can just use NANDs.
Should we use our ors and nots made of NAND?
So it's not wrong to do that, but the spirit of this is there's just NANDs to really, so partly just pedagogical to emphasize that we really only need NANDs to do anything we want. Yes?
So the only case that we want to return false is where A is true and B is false.
Yes.
So what we can just say is NAND of A and then NAND of AB, or BB, I think. So we're making sure that we're returning not the case where A is true and B is false, meaning that you want to, I think it's NAND of A and NAND of BB.
NAND of A, NAND of BB.
NAND of A and not B.
Let's try it.
Maybe it's the other way around, I'm not sure.
All right, what do we get?
Yep.
Yay, nice. So this is the truth table for implies, right? A is true, B is true, it's true. If A is true and B is false, it's false. If A is false, no matter what B is, it's true. So why is it important that we can do everything with NAND or with NOR? We can do the same thing with NOR with different formulas. Why is it important? Why is it cool? Yes?
You greatly reduce the size of the actions that you take if we're thinking about this AI problem.
Yeah, we don't really need all that many primitive operations to do stuff. However, there's kind of a cost to that. And what's the cost?
They can get really complicated.
Right. So if I am doing implies, I have to call NAND, or let's say I have to call NAND 3 times to do one OR. It turns out, do you guys take like hardware classes?
No.
No, not at all. Well, it's worth knowing. I think like one of the coolest things about this is it turns out in hardware, when you actually make a chip and a transistor, they actually leverage this a lot. Everything is made out of NAND gates. So like when your Intel chip is running computation, the way that they implement ands and ors and nots and implies is all out of NAND gates because we know how to make a NAND gate out of transistors and MOSFETs and stuff like that. I don't really know how, but like technology knows how to do that. So this fact that NAND or NOR is primitive is like primitive. It's all you need to get all the Boolean logic is really nice because the hardware people only need to make one gate and then we can wire it up in different ways to get all of the operations that we want. So it's kind of fun. Okay. So it's nice so it's sort of conceptually elegant. And it also kind of mathematically leads us to this search for like what is the bare minimum of what we need in order to do inference. Of course, in practice, as you guys have tried to encourage me to do while I was doing the coding, we actually have these higher level operators. And what's nice about them in terms of the action space is it lets us search deeper. In one move, and even though maybe our poor transistors are doing more things because it's all NANDs at the end. In one move with an OR function, we can move several NAND operations deep in the search tree. And as you get to more complicated theorems, so there's a finite number of 2-nary and 3-nary of any operators. But as you add more and more theorems, you can move deeper in the search tree quicker, right? So this is why it's worth knowing things. Instead of just knowing the rules for NAND, because you can leverage that to go deeper, faster, farther, louder, harder, faster in the search space. All right. So the next thing I wanted to do is kind of play this game. Who's ever heard of Lewis Carroll? Some of you? So why is he famous?
Alice in Wonderland.
Alice in Wonderland, yeah. He was a mathematician, and he had a lot of fun coming up with what are called logic puzzles. So what this is an exercise in translating between English and a little program, a little world in deductive logic, and making inferences about that world. So he actually published, there's like on the internet you can go find whole lists of these little problems. Some of them have like 10 different formulas. So we're going to do this one together in class, and then we're going to break out into little groups and do one on your own. What's that?
How is a raven different than a writing desk?
What's that?
How is a raven different than a writing desk?
There's no answer to that one.
Yeah.
Yeah.
Yeah, that's fine.
So that's not quite what this is.
Okay.
But he was also very fond of jokes and wordplay. The joke of that riddle is there's no answer. Nobody knows what the answer is. Why is a raven like a writing desk?
Yeah.
Yeah. All right. So let's do this puzzle. So what you're given, and he was deliberately making these kinds of fanciful so that you can focus on how the rule you're supposed to apply the rules of deductive logic pretending like you're a computer rather than using your intuitions about it. So it's a very fanciful little puzzle. So the theorems are all babies are illogical. Nobody is despised who can manage a crocodile, and illogical persons are despised. So, and what you're supposed to do is combine these inferences together to get a single statement at the end that is the solution to the puzzle. Okay? So how can we do this? Using the rules of deductive logic. What's that?
The first thing is to notice that all babies are despised.
Yeah, so right, so that's the that's exactly the chain of reasoning that we need to do. But how can we let's try to write it first of all in a way that makes it easy to see those kinds of connections. So what can we do to do that? Yeah.
Replace all nouns with just arbitrary
Symbols. Yes, that's exactly right. So what we're going to do is come up with the sort of primitive statements in this little world that he's created. So what's one primitive statement that you could come up with? Proposition. Yeah.
B implies I. Something like
Well, what's B and what's I?
So being a baby implies that being illogical.
Yeah, so I'm asking for something even more basic, almost. So you said B implies I. So B is a symbol.
Oh.
What does that map to?
Being a baby.
Being a baby, right. So we can, I think that's the first one. Yeah, B is, it is a baby, okay? So now what are some other symbols in here without doing the, we're going to get to the implication, but without doing the implication, yeah.
I illogical.
Yeah, so I think I called it L, but yeah. L is, it is logical, okay? Make sense? So what's another one? Yeah.
Despised.
Despised, something is despised. I think that's, oh, no. All right, so my order is wrong. So despised, and finally, it can manage a crocodile. All right, so now we have these sort of primitive statements. Let's try to translate this first one into a logical expression without, not just all and ands. Let's try, we can use implies and ands and ors and things like that. So I heard you say it before.
So B implies I.
Yeah.
Not
Not L. Yeah. B implies not L. Does that make sense? So what we're doing here is we're reading this sentence and we're using our unique human language capability, which we don't know how to make computers do. And we're converting it into this symbolic language of B implies not L. So how can we do the next one? Yes?
M implies not D.
So nobody is despised who can manage a crocodile. Yeah, I think so. Let's see if that's what I thought this morning. Yes, good. Yes, M implies not D. So M is it can manage a crocodile. And if you can manage a crocodile, you're not despised. Okay? It's a kind of archaic syntactic structure, but there you go. What's the last one? Illogical persons are despised. In the back?
Not L implies D.
Not L implies D, yeah. Nice. So now what you can do is make these chains of inferences. So what's one inference chain we could make from this? So what you're supposed to do is combine them together. So yes?
B implies L, and not L implies D, so B implies D.
Yes. Does that make sense? So B implies not L, and not L implies D. So you can say B implies D. What does that mean in words? B is... Babies are despised. That's so sad. All right. So B implies D. So what else can we do if we have B implies D? Because what we want to do is use all of them. So how can we use this one? Yes. Why is that the answer? Or why is that a true thing that can be inferred from these axioms, these propositions? Yeah. So first we can convert this to the contrapositive. So we can say D implies not M. Does that make sense? We're kind of doing it in our heads. And then we can take our first one and get B implies M. And what's that in words?
Not M.
Not M, yes. B implies not M. So what is that in words? I think
Take your baby and put it in front of a crocodile.
Yes, maybe that's it. But like using their words, their axioms. B implies not M.
All babies can't handle a crocodile.
Yeah, babies can't handle crocodiles. Yep, babies cannot manage crocodiles. Does that make sense to everybody? Is that the only thing we could have inferred from this? No. How many things can we infer from this? Yeah.
You can also do that. Anyone who can manage a crocodile is not a baby.
Yeah. So is that the only thing? Or is it like, could we?
I don't know. It's two.
Are there other things?
A crocodile cannot be managed by a baby. Is that kind of a different one?
Yeah. Yeah.
Yeah, so like if you allow arbitrary negation, for
Yep.
example.
There you go.
Not crocodiles can not
Yes.
be managed by.
Yes. Does that make sense, everybody? So given these axioms, I can just start generating true statements till the cows come home. Using this, even just with negation, I can just say not, as long as I want. So part of this is, and if you're running like breadth first search in this space, I'm going to show you some code that does that next. If you're running breadth first search in this space, you can just do that, and people do. And there's a lot of work in AI, in theorem proving, and doing this in smart ways where you're trying to find the right theorem or the most elegant path to a theorem or the ones that are interesting. But the sort of raw search space of this looks a lot like the search space for all of Python, all Python programs, right? You get not, and it may all be true, but it may not. It might not be very relevant. So the next thing that I want to do in class is just take a few minutes and have you guys do another one of these puzzles on your own. So this is another Lewis Carroll puzzle. It's kind of fanciful also. So why don't you take 3 or 4 minutes, turn to a partner, and try to write down what you think that he's trying to get at through this problem. And then we'll do it together. Go.
So, shall we write it out and try to get form first? So, C, let's say the terrier.
Everything that wanders among the
Among the signs.
areas and outliers. So terrier cannot have
Let's do you.
It's okay to write things down as you're doing this.
How was your
Do not wander among the
Let's keep the knots in there. So not
You're saying not
Nothing is common that don't wander among
I think it's things that you don't want to among the sides of the zodiac.
I think we've got
I think
not seen implies not seen. What is this saying? So I'll call that.
I don't know whether that's true.
What's that?
Well, I mean, I don't know if you actually could have this. Like, if the end result like actually is, I don't know.
So the point is not what's really true in the world, it's what's true, yeah, yeah.
Really?
How many of you guys have the answer? How many of you guys want more time? All right, 1 more minute.
So, nothing but a carrier in the tail. We can come up with lots of crazy implies here. That's not really can you get that? You're not a carrier.
There's something really tricky that missing somewhere.
Hey man, are you in this class?
Oh wait, no, sorry. That's wait, comment is A. Comment is A.
All right, guys. Finish up. What's the answer? Hey. Hi, guys. What's the answer? Who wants to shout out the answer? Yeah? No comment is curly-tailed. Yeah. So why don't we try to derive it in the same way that we did before? So what are the fundamental theorems, or what are the sort of fundamental propositions that they're using here?
Terriers don't wander among the signs.
Well, let's get the basic one, right? So something is a terrier. Yeah. What else? Let me write this down on the whiteboard so we don't get in trouble. The order's wrong. X is a terrier. What else? Yep.
X wanders among the signs of the zodiac.
Wanders among the signs of the zodiac. Okay, what else? Yeah.
Being a comet.
X is a comet. A comet. What else? Somebody from this half of the room.
Has a curly tail.
X has a curly tail. X has a curly tail. All right. So here we go. All right. So now let's translate. If we call this, is it the same order? A X wanders among the signs of the zodiac. B, C, D. Oh. Good. Okay. So now let's translate our first proposition into our first sentence into an expression in deductive logic. So no terriers wander among the signs of the zodiac. You raised your hand?
Or the same. B implies not A.
Okay, so B implies not A. So B is, it wanders among the signs of the zodiac, and if it does, it's not a terrier. Yeah. Okay, what's the next one? How do we translate the next one? Nothing that does not wander among the signs of the zodiac is a comet. There's lots of negation in there. Yeah? Not B implies not C. What do we think of that? So not B is X doesn't wander among the signs of the zodiac, and not C is X isn't a comet. So nothing, so it's not a, if it, so if it does not wander among the signs of the zodiac, it's not a comet. Yeah, that seems good. And then C, nothing but a terrier has a curly tail. How do we do that? B implies not A. Let's write that down. B implies not A. No, D. D.
I think D implies A.
D implies.
I mean,
D implies
yeah.
A implies B.
I'm just writing what you say. I haven't checked it. Yeah?
And A implies B.
Say it again?
And A implies B.
Yeah, because if it's a terrier, it has a curly tail, and if it has a curly tail, it is a terrier.
Nothing but a terrier. Yes. So A implies D. D implies. No?
Not A implies not B.
Nothing but a terrier. So wait. So D implies A says it has a curly tail, implies that it's a terrier. So not A. A implies not D. Yes?
Which is the same thing.
The same thing. Okay, so now how can we combine these statements of inference? We have to do some contrapositivity. So we could say B implies not D. Is that good? And not B implies not C. What? Yeah?
Not, sorry, A implies not B.
A implies not B. So A implies not B. That's contrapositive off of that. Yep. Good. Yep, I think that's true. And what's that in words? A implies not B. So X is a terrier implies X doesn't wander among the signs of the zodiac. Yeah. What else?
Well, we
Yeah.
already have not B implies not C, so we can say A implies not C.
Not B implies not C, so we can say A implies not C. So if it's a terrier, it's not a comet. That's good. Sounds good, right? What else?
D implies not C.
Okay, D implies not C. D implies not C. Why? D implies A implies C, not C, so D implies not C. So D is X has a curly tail, so if you have a curly tail, you're not a comet. Comets don't have curly tails. So, let's see. So here's the inference rules.
Unless you've got a terrier named Comet.
No comet has a curly tail.
Comets are not terriers.
Maybe terrier is called common.
So you guys are really bringing up interesting points. So this is true only if you accept these initial statements, right? If you pick different statements, you can get completely different answers. And when we step back and translate it back into English, you're suggesting new axioms and new things that, like, or corrections maybe to this kind of fanciful world that change what we get in the deductive logic algorithm. So this kind of like mapping between what we want, like this, we sort of seen this mapping before when we're defining our state and action spaces, right? Once we get it into this formal language, we can write a program that tells us how to get more true statements from the true statements, but we can't really tell it what to start with. We have to think and use our judgment as people in order to do that. And that's going to be true forever, I think. So this sort of translation from the problem that we really care about to the problem that the computer can do something with is one of the biggest unsolved problems in AI today. And a lot of, and what I don't want to do is just brush it under the carpet. So that's kind of why we're spending some time doing these little exercises. The reason that he picked these examples where, who terriers and comets and babies and crocodiles and stuff, is to try to help, these were exercises for students to try to focus on applying these rules of inference without using extra knowledge that you as a person put into the system. If you put extra knowledge into the system, you have to encode it and then let the rules of deductive logic run. So now what we're going to do is talk about what it's like to actually have a program that does some of this deductive stuff. So I wrote one this morning. Deduction. All right, so so let's have some statements. There were 4 shots fired. There were 3 shots fired.
Maybe like a function predicate for a number of shots?
Yeah, we could do that, but I don't want to get into that. Yes, you could put more fancy stuff, and a lot of the world of people talk about different types of logics. They'll put more stuff into your logic to make it more powerful, and so you don't have to have as many statements. But for now, we're just going to say we're just only going to consider 3 shots fired and 4 shots fired, and how about D? Is JFK was killed by a conspiracy. How do you spell conspiracy?
Wasn't that not A?
Yeah.
What's that?
Isn't that not A though?
Well, it's that's a good question. Is it not A?
And there could have been lots of independent shooters at the same time that were not working together.
There you go. Yeah. So maybe not. Maybe not A implies, well, it sort of depends what you mean by not A. A implies not D. Do we think that?
No.
I think
Because Oswald could have acted alone, but not actually killed JFK.
Yeah.
Exception or something.
What's that?
Maybe he had a one-man show.
Yeah. So let's say Oswald acted alone and killed JFK. And fired, I can get this connected as you want, and killed JFK. So now, do we think A implies not D? Maybe? Yeah. We could, so we can play this game of adding more edge cases forever. And it's not that they're wrong. It's again, we're exactly in the space we were with our state action spaces, where we're defining how big our state space is, and we as people are trying to make it focus on the ones, the propositions we think are most relevant. And whether you're doing deductive reasoning or probabilistic reasoning, that tuning of the state space or tuning the sample space to focus on the stuff that's interesting and not the aliens landing on the Texas Book Depository, as an extreme example, is part of you taking your knowledge and applying it to the problem. So now, so now we have some theorems. So here's a knowledge base, which consists right now of just A. So I can also make more complicated theorems or propositions out of this. So what I did was just define some propositions, implies and or not. And they're just little data structures. So not contains a position and it has a string, so it can print out what it actually is. And so if we want to, we could say A and not A. What's wrong with that? It's inconsistent. Yeah. So it's a state of affairs where A is simultaneously true and not true. So what that means is that you can prove anything you want, because you basically get to, it's like dividing by 0. So we don't want to do that. But maybe we want to think about it one of our implications. So what were we saying? Oswald acted alone and killed JFK, and JFK was killed by a conspiracy. So what can we say about that as an implication? Yeah.
3 shots means Oswald acted alone.
Let's just use A and D. We'll get to more.
A and D.
Yeah.
It implies not D. Is what you said?
Yeah. So A implies not of D. All right. So now let's try to run it. So what I'm doing right now is printing out the knowledge base of what it knows. So Oswald acted alone and killed JFK. And if Oswald acted alone and killed JFK, then not JFK was killed by a conspiracy. Does that make sense? So it's just printing out in words these two facts that we encoded here in the knowledge base. Yes, I see nodding. And then what we do is basically doing breadth first search. We have a method to get successors. So I have a 1 argument successor and a 2 argument successor.
And it's still by.
What's that? No, it's doing raw input, so it's waiting for me to hit enter. So what's going to happen when I hit enter? What do we think should happen?
It should print out the same 2 again and 1 more.
Which one?
Or 2 more.
Which one do we really like for the using our judgment as humans? What would we like to see? Yeah.
Not JFK was killed by a conspiracy.
Yeah, not JFK was killed by a conspiracy. So we like it to use modus ponens, right? Like this should match, so therefore we should be able to know that this is true, right? Is that the only thing we could prove though? Like could? Yeah, I see you shaking your heads, right? So it's just like before, we could add nots and ands and get infinitely many other possibly less interesting inference statements. So right now, if it's, yeah, good. So right now I have added no rules of inference to this. So it's just going to do nothing. It's not going to add any new knowledge to the knowledge base. So let's go and modify our successors here. So it actually gives us a new inference. So here we have 2, what's that?
Great function.
Yeah, it's a 1 argument and 2 argument Python. I don't know. I could have done it a different way. I was just trying to get to the essence of it. So we have 2 propositions in our knowledge base, and we want to encode a programmatic version of that modus ponens rule, right? So if A, so let's write it out on the whiteboard. How much time do I have? 5 minutes. So we want to say A implies B, A therefore B. Okay? So how can we code that up? So when is this rule going to apply?
It isn't A implies B.
Yeah, so if is instance, P implies, then what else has to be true if we know what it implies? Not you. Yeah.
We want to know what's implying, so it finds like what implies what.
Right, so we can say P.P1 and P.P2, and P1, so if it's in location, P1 is A and P2 is B. So what do I want to do to apply this rule, yeah?
Not P2 implies not P1.
I could do that, yeah, I could take the positive and make that, but we're going to, and I could do lots of other ones too, but we're going to do this one. What's that? Yeah, that would be a 1 argument more, you're right, yeah.
Then if Q equals P.P1,
Yes.
then P2.
Yes. So if Q is P.P1, then results dot append P2. Does that make sense to everybody?
P.P2.
P.P2, thank you. Let's try it. All right. Whoa. So we solved the JFK murder. So does that make sense? It checked if this was equal to that, and we inferred something new that wasn't in our original knowledge base. It was sort of buried in this implication. Well, it was implied by it, and we kind of did our deductive reasoning and figured out something else that was true. So this is sort of basic theorem proving. We could, and as you alluded to, we could add other rules. So we could add the contrapositive inference to this in the same kind of way. So I could say if the not if I have an implication, then the not implies the not. The not of P1 implies the not of P2. And something implies, if something is true, then its double negation is true, for example. And if 2 things are true, then their and is true. And you can just keep going and derive more things. And this is sort of, and as I said, there's lots of work that does many more complicated versions of this, adding different rules, and there's kind of a fundamental rule that the textbook talks about that you can get to this. But what I want you guys to take away from this topic is that we can encode knowledge in a computer and have an algorithm that actually does come up with these proofs. The path that I took in my search space is the actual proof. It's the rules that I followed of deductive reasoning. And the goal that I got to is the actual statement that's true in the world. And just like in our Lewis Carroll examples, it's kind of garbage in, garbage out, right? So if I put good stuff in my axioms, then it's gonna produce good output. If I put axioms in that don't make sense, then like A and not A, or even something like in our JFK examples, like we not even thinking about like what if aliens came or something else, then we don't get good results. So for that reason, these systems are sometimes called truth maintenance systems. So if you start with something that's true, it'll find more things that are true. But if you don't start with something that's true in the first place, you're in trouble. Okay. All right. So now we're going to start to, so this is sort of the shift between deductive reasoning, where you can imagine putting in all of our facts about JFK, and the probabilistic reasoning, the plausibility reasoning that James is talking about. So particularly, like this is quoting from the report, it says, establishes a high probability that 2 gunmen fired at President JFK, John F. Kennedy. But in either case, we can't know for sure. And we have different people looking at the evidence and running some kind of inference process and coming up with beliefs about what they think might be true about the world. And so what we're going to do is extend our logical reasoning in the next class to handle reasoning about different degrees of belief. And what's kind of amazing is you can basically, what James kind of goes through in the book, is that you can start out with what seems like very intuitive and common sense he calls them desiderata, that we would like for our rules about reasoning about degrees of belief. And this is what they are. So first of all, he says degrees of plausibility are represented by real numbers, which are going to turn into our probabilities. So that sounds pretty hard to argue with. We have something we want to compare with different quantities. We're going to use a number to represent that quantity. The second rule is what he's calling qualitative correspondence with common sense. So we'd like it to be the case that if you disagree, if a rational person disagrees with what these rules do, and you show them that disagreement, the rational person would like to revise their thinking. And another way is sort of intuitively, it corresponds to those rules of plausible inference, those modifications of modus ponens, where the deductive reasoning was just ignoring them. It was not able to say anything about those cases. We'd like to be able to use the information to make our updates about what we believe. And then he has these 3 sub-rules of consistency. So first of all, if a conclusion can be reasoned out in more than one way, then every possible way should lead to the same result. So another way of saying that is if there's something that's true and you can follow 2 paths through the space to get to it, you shouldn't be able to prove A and not A in the same space. But now we're talking about real numbers. So if I can conclude that my degree of belief in something is A using one line of reasoning with my axioms, which I'm going to pick to be whatever I want, there shouldn't be another line of reasoning that comes with a different number for that value. So consistency. Otherwise, how do we know which one is the right one? Second, we want to take all of the evidence that we have into account in doing the reasoning. So we're not going to just arbitrarily ignore information. It should take into account all information that it has when making its conclusions. So that's hard to argue with too. Why should you throw away information? We'll talk about why you might want to, but at least mathematically, we should be able to reason without doing that. And finally, we want to represent equal states of knowledge by equal plausibility assignments. So since we're going to use these numbers and we're going to compare them, we like more now. If we know the same, we want to have that same number for the state of knowledge. And what we're going to do next class is talk about how you can take these desiderata and get all the probability, the sum rule, the product rule, uniform distributions, and zeros and ones, and everything else, just from this. It's pretty cool. All right, thanks guys. See you on Tuesday.
I think you should try denying each of these. Wait, so like if you deny the bottom,
Hi.
the bias, right, like, which has